Yeah, good evening, it's Charlie ZL2CTM. Well, I just wanted to do a follow-up video from the one I put up just before on this classy amplifier. I've done some more reading online and watched a few videos on some of the theory, and while I'm certainly in no way, shape or form an expert in this, I'm starting to get a bit of understanding of what the various components are doing by way of the waveforms and that. So I've reconfigured this amplifier, and I'll talk it to a sec. But what I did come across was, I just mentioned before, some good videos that talk about what various components do. And what was quite interesting, before I get into what this is, was that inductor there and the need for it to shift the waveform, the current waveform that is, to make sure that it falls to zero as the switch is opening and closing. So that was certainly useful. But this is another interesting paper that I came across. So I might just put that camera down just a little bit there. So this was a paper from a guy called Bill Slade back in 2010, called Notes on Designing a Classy Amplifier, or Classy RF Power Amplifiers. If you search it on Google, you'll find it. And he talks about, in this particular paper here, building upon the original paper that we saw back here from Nathan Sakel and his associates. And I really liked this particular paper here. It sort of resonated with me in terms of what he was describing and what the various components do. So I elected to take this. I've turned these formulas here, which we'll cover in a sec, into a spreadsheet, which allows me to sort of more quickly use it. And like I say, this amplifier over here is using the values out of this. Now, the paper itself is full of derivations that comes up with a series of formulas to work out these various components. I elected to use different names for the various components, and I've just used values which sort of mean something to me, like C parallel. I've called this C extra, so this is the extra inductance, which I'll talk to in a sec. This is capacitor for resonance, L for resonance. The dotted line there, this is what the switching device sees as its load. We have an L network here, so this is a matching network, so L matching and C matching, to transform the load, or the amplifier load, which I've notionally called Z here, noting that I'm not worrying about the reactive component, so it's just purely resistive, transforming that back to be what the switching device wants to see by way of its load. Anyway, so these are the values that I have settled upon. And like I say, it just works through a series of formulas that he's derived to come up with various values. So the first one, and just sort of noting before I go any further, VCC of course is our voltage at the top, voltage collector, which will be 12 volts in this particular case for the worked example over the page. PO, or power out, that's how much power we want to dissipate in our load. F is our frequency of oscillation. In the worked example, it'll be 3.525 megahertz, and later on we've got a Q down here, which hopefully I won't forget, that needs to be greater than 5 to 7. Anyway, I will put all of this up on the blog, so there's no need to copy it down. So yeah, like I say, all up on the blog. So first things first, working out what the device wants to see by way of a load, which I'm just calling RL here. So again, I won't go into the details because it's just no point. It's going to be reading out numbers, but there goes the equation there, and you'll come out with RL. We can now use that in the next formula here to work out the current IO, so the average DC current that's passing through that particular device. Now, a note here that the peak current that will be passing through here will be 3 times our average. So that's a value you'll need to keep an eye on later on down track, once that's derived, when you select that particular device. So I'm going to be playing around with an RF510, so I know that I've got 5 amps to play with. The next one is C total. So C total is the sum of this parallel resistance plus the output capacitance of the device. And in the case of an IRF 510, we're talking 81 picofarads. So when you work out the C total using our frequency and our VCC and our I/O, so you can sort of see this cascading as you derive one component that's used later on and further down, you get this total capacitance. So therefore the actual value of that device there is C total minus the output capacitance of the device. We now have coming up as L extra. So I've called it extra because it's the extra inductance that's required to shift. If you look at online at some of the very good videos, and I won't try and explain it because I'll just do a very poor job, of that extra inductance required to shift the current waveform. So that's notionally called L extra. And that's the expression there for that. We've now got C res. Now this is quite interesting too, because I came across a few warnings in various papers that talk about class E amps, saying don't be fooled into thinking that series capacitor and the inductance is a series resonance circuit at the frequency of oscillation. And it makes a whole lot of sense why they said that when I look at this particular approach taken by Bill Slade, because that inductor is made up of not just the inductance required to create the resonance, but also these other components here, that extra to get the phase shift, and later on, as we'll see, this matching inductance here. So right or wrong, that sort of resonated with me, and I could sort of better understand why that had been said in other documents. So C resonance here, so there goes the expression there. We're now introducing Q. Now Bill says in this particular paper that it should be greater than 5 to 7. He then goes on in his particular example to use a Q of 10, which I've used in this particular amplifier here. So that's the expression for the inductance. So that's that L res there. We then move into the matching network that I just mentioned before is required to match that whatever the load is to equal what the device wants to see by way of a load, and that's the expression there. So yep, nothing special there. The inductance for that, so now using that matching capacitance times RL and Z, and then as I just mentioned before, L total, so this is the total inductance that will then be used to wind on a particular core to come up with the required inductance, and that equals that extra inductance we worked out here plus our resonance inductance here plus our matching inductance there. So that's our one large lumped L total that I've called here. A couple of other points that are made in that particular document. The RFC, that's that blocker up there from the VCC down to the device, its inductive reactance, 2 pi FL, needs to be greater than 10 times RL. There's also another caveat that there needs to be no self-resonance by virtue of the fact that it's got windings and therefore there's interwinding capacitance, to make sure there's no self-resonance between the first and the fourth harmonic. What I did, I wound that particular RFC there. I then put in series with that a 50 ohm load. I then put that across the SIGGEN and swept it, and just looked for any changes in amplitude across that frequency range. And the other thing which he talks about is the maximum voltage that's going to be seen across this device is going to be 3.5 times VCC. So that's another limit, I guess, or another value that needs to be borne in mind when choosing a suitable device for this. So having now sort of, like I say, I won't go into the derivation of those, that's all on the paper, but having now said that, I then use those formulas to come up with an amplifier. I used VCC at 12 volts. I decided to go with a power out of 5 volts, let's say again 5 watts. I note others have mentioned in various derivations and formulas and examples that in their experience they aim for I think one person said even like 150% of what they wanted, they designed for, because that's what actually would turn out. Right or wrong, I've just run with a power out of 5 watts. Frequency of oscillation, as I just mentioned, 3.5 to 5 megahertz, and I've used a Q of 10. I'm going to try and use again the RF510 because I've got quite a few of those lying in the box, plus a MOSFET driver, and I'll talk to that in a sec, what I used in the end for that. And because I'm using that RF510, as I just mentioned before, its output capacitance is 81 picofarads. Its maximum allowable voltage across the drain to the source is 100 volts, so big tick there, because that's less than 3 times or 3.5 times our VCC. And its max continuous current through it is 5 amps. Right, so no point reading this out because I think it's more interesting to see the actual waveforms themselves. So plugging in the various values, working through the sequence of formulas, I come out with various values. An RL of 16.6, an output current of 0.417 amps, therefore 3 times that equals 1.25, which is less than that, thumbs up. I come out with a total capacitance, I then subtract 81 puff to come up with that value. I come up with my 3 values of inductance, as well as our series resonant capacitance there. Again, I won't go into it because it's going to bore you with tears there, or bore you to tears. Suffice to say, that overall inductance came out to be 9.4 microhenries. I have in the junk box an FT68-2, which already had something like 38 turns, so I just added a few more to give me, if you use the online toroid calculator for that, 9.58 microhenries, and I just increased the spacing a bit while looking at it on the LCR meter and got that down to 9.4. Anyway, so the only other thing I elected to do is I didn't have much success at all in trying to use the MC34151, I think it is, the MOSFET driver. So in the end I elected to use just a very simple totem pole driver. So a 3904 and a 3906, so an NPN and a PNP, strung between 12 volts and ground. On the base side, the tied bases, I just used 1 k ohm, being driven by the 5 volts from the SIGGEN, and the output, the tied emitters there, just through a small 4.7 ohm resistor leading into the gate of the MOSFET. And that's what's just hiding over the back there, that little totem pole driver there. So, what else is worth discussing here? And we'll see it in action in a sec. In the end, that series, that C series, it wanted to be 271 picofarads. I built the amplifier and tested it, and through a little bit of trial and error I reduced that, so I've now got sitting there a Sega a 220 picofarad capacitor in parallel with a small trim capacitor which has a maximum capacitance of 54 picofarads, which gave me the ability then just to tweak that value there. The output C total there hasn't changed, just 2 capacitors there because I couldn't quite get exactly the right value, so I just found 2 in the junk box to make it work, and same with that what I'm calling C matching. So there's the which goes from the from basically that low to ground. And the only other thing too which I've left in circuit for this is that 1 meg ohm resistor from the gate to ground. I found if I didn't have that, I was losing quite a few MOSFETs. They were just basically giving up the ghost and deciding to go somewhere else. So you know, by adding that small, I guess it's a bleed of some sort, it's just that sort of mortality rate has dropped right off. So that's so I'm going to leave it in circuit, and it is left in circuit. Other than that, no change. So we've got our coming through that little micro switch there. We have our SIGGEN square wave coming in through the totem pole driver and into the gate and through here. So what I'll do now is I'll just reposition the camera so we can see the SIGGEN and the meter. So hopefully that's all in view there. Let me just, yeah, that'll do. So that meter there is monitoring the voltage drop across that 0.1 ohm resistor. So whatever I see, as you'll see, for example, 10 millivolts would then be 0.1 amps, 100 milliamps. So up on the scope there, let me just see, we've got 12 volts coming on in, and let's arc that up. So we'll see two traces. We'll see the yellow trace, which is the voltage across the 50 ohm load, and the purple trace is the voltage across the MOSFET. And before I go any further, what I'm going to do, okay, right, I think that sort of sets the scene. Right, so moving forward, like I say, I found that I had to reduce ever so slightly the capacitance of that series capacitor between the drain and the inductor, and we'll see that. And I did that because we had the old little ski jump here, as I've called it, and if we look at that original paper from Nathan, he's got that very useful chart we saw in the last video. Hopefully that's viewable there. And I was sitting in here. So I had this, what I've just called a ski jump trough, and as it says here, increase C2. I found that I had to reduce it slightly, which basically got things resonating nicely, because before I did that, I found for whatever reason that the power I was getting out was in the region of 2 watts, in fact less than 2 watts. It just wasn't performing at all. Having done what I've now done now, so with that 220 plus that 50 picofarads in parallel, which arguably comes up to the same value as the design spec, I can tweak that, and you can see that sort of that little knee there coming back up, and you see a few things going on there. So you see the so interesting enough, if I get it really bad, I'm getting 19.36 volts RMS across that 50 ohm load. So let's just round that to say 19 volts. So 19 volts squared divided by 50 comes out at 7.22 watts. And if we look over here, I'm getting 90 millivolts. So 90 millivolts divided by 0.1 ohms comes out at 0.9 watts. Let's say again 0.9 amps. So 0.9 amps times 12 volts, which is the VCC coming in. You know, I'm now consuming 10 or close to 11 watts of power from the battery, in this case, or the power supply. But I'm getting 7 watts out. So 7.2 watts out. Let's round that to, well, I use 10.8. 10.8 divide comes out at 66% efficiency. I understand where, from a pure theoretical point of view, efficiency should be, you can theoretically get up to 100 odd percent. I understand in reality it's more like sort of the low 80s or 81 odd percent is more realistically on a really good day. Full stop. So what I'm going to do, I'm just going to well, I could leave that at 7 watts, which is quite nice, or I could drop that down to say 16 volts, and see the waveform there. The voltage across the device is looking better and better in terms of the ideal. And I'm now down to 16 volts. So 16 volts again squared, 50 divide should be more like 5 watts. And as we can see here, we're drawing a lot less current from the power supply. So if I was to, just for interest's sake, bring that up to 5 watts, which is sort of roughly, I've gone a little bit too far there, but close enough for government job, 16 volts. We've now got 66 millivolts, so 0.66 amps, so 0.66, 12 times that, so 5 now divided by that, I've now got an efficiency of 63. So all things being equal, that was actually slightly higher. That's 16.29, but it seems to be that either way we're getting roughly that sort of 66% efficiency. So why not, go for gold and eke that out to sort of 19 volts there, 19 volts RMS across that load. Sure, I'm drawing now 93 or 0.9 amps, but if my efficiency is the same as what I was getting at 5 watts, why not? That current is still way less than what the device can handle, which is 5 amps. The voltage across it is 50 volts, so I'm allowed up to 100 volts on that particular device. So as you can see there, sorry if that wasn't all in shot, let me just come out a little bit. No, I can't, sorry. Shucks, 7.2 odd watts from a single device. That doesn't seem to be too bad. So let's make sure that's the same. That just fell off. Yep, no, that's all the same. So final thoughts. I'm not quite sure if I should try and do any more to try and eke out greater efficiency. Yes, I'm going to be taking this portable, not so much into the bush. I'll be taking, it's more of a portable radio for when we go for things like triathlons and that. So I've got more of a small motorbike battery, a 12 volt lead acid battery, which I'll be taking. So I'm not too concerned that the efficiency is not right up there. Gosh, what else to say? I think looking back, the addition of that totem pole, maybe just a bit of zooming up there, so a bit of interest. I think the addition of that totem pole driver there was certainly a good way of doing it. I'm not quite sure if I wanted to change that in any way. So I think that was a good addition there, just to drive that MOSFET would appear a lot harder. It seems to get better performance than I had just driving it directly from the SIGGEN. I think I could probably get away with, purely from a protection point of view, get away from having those two Zeners, those two back-to-back Zeners there. Well, not back-to-back, but series Zeners over the back. You probably can't see them there, they're just loafing there. I could probably do away with that, because I'm clearly not getting anywhere near a dangerous voltage level for that particular device. So that would save a couple of components, and as you can see, that's it. So apart from the low pass filter there, again, I'm not an expert in any of these, but a 7 odd watt amplifier with just a handful of components, and that's cold. Cold is a cold thing. Sorry. Absolutely no heat at all on that. Nothing. So you could get away with that having a much smaller heatsink, which would make a small portable amplifier even more realisable. Anyway, so I will probably say 73s there, and leave it for now. If I got anything wrong there, please sing out in the notes. It's all for all of us to learn, including myself. And I certainly welcome constructive feedback for sure. So I certainly welcome that. I think moving forward now, it's a matter of getting out the radio, which is hiding over the back there, tidying this up, and mounting it on that, and then start to look at going forward, I think. So I don't think we're too far away from having a functional transceiver, which would be good. Start to build that CW back up again. Rightio. I think that's what I covered. Like I say, I'll put things up onto the blog so they can be used. And I'm now starting to ramble, which is a good clue and a good hint for me to wrap this up. Anyway, 73's all. Stay safe, and we'll see you next time. Cheers all.